Welcome. In this video, we will discuss Euler's method. Euler's method is a technique for finding numerical approximations for solutions to certain types of initial value problems. Initial value problems are differential equations where we are told a specific point that the solution curve passes through. For this section, we will use first-order differential equations of the same form that we used when we were studying slope fields. So the differential equations have the form y prime equals some function of x and y. We are also given an initial condition. The initial condition can be thought of as a point that the solution curve passes through. The x0 is the x value of the point, and the y0 is the y value of the point. So we have a differential equation, and we have an initial condition, which is the same as a point that the solution curve passes through. For this video, we won't algebraically use Euler's method, but we'll look at the graphical concept of what Euler's method does. Let's start with an example. Here we have the initial value problem y prime equals x plus y. Here's our differential equation, and here is our initial condition, y of 0 equals 0. This initial condition simply says that the solution curve passes through the origin, 0, 0. Here's the picture of the solution curve for this differential equation. There's the slope field with the solution curve passing through the origin. And we're zooming in on this small section near the origin to better visualize what Euler's method does. We want to use 4 steps of Euler's method with step size 1/2. Now, we still haven't discussed what Euler's method actually is, so let's talk about what Euler's method is. To do Euler's method, we start at a given point. We start at the initial point that's given. And we move some step size in the x direction. Here we're told to move 1/2 in the x direction, and we move following the direction of the slope field at that point. Now, I look at where this line segment ends, and from that point, I draw a new line segment going an x distance of 1/2, and I follow the direction of the slope field at this new stopping point. Now, we don't have a line for the slope field here, but we can imagine that it's something between a slope of 0 and a slope of 1. So the line could look something like this. I go an x distance of 1/2, and then I stop. Now I reevaluate the direction of the slope field. Now I have a slope that's a little bit between this slope and that slope, so I go just a little bit steeper. Once again, an x distance of 1/2, something like that. Now I reevaluate, and I think what the direction of the slope field is here, a little bit steeper yet again, and I draw a new line segment, once again in an x distance of 1/2. This sequence of line segments is sort of like the solution curve. It's an approximation. And if I picked different values, if I picked these different points, these points would be close to points lying on the actual solution curve. Graphically, this is what Euler's method does. We start at the initial point, and we follow the direction of the slope field for certain distances, plotting new points as we go. In this way, we obtain a rough sketch of an approximation to the solution curve. Now that you know the graphical concept of Euler's method, you will learn how to find these points algebraically in class.